start the derivatives, which I said we would do in this class, I just want to make a comment on what are called as projection tensors, which are very useful in many applications. So let us see what this projection tensor is. Let us say that I have a vector u. Okay, now I want to resolve this vector, say in the direction of E and in a direction perpendicular to E. Okay, u parallel to E and perpendicular to E. So what I do is very simple. If I want to have u say parallel to E, then this is nothing but u dot E. Okay, so if you look at that in indical notation, then this becomes ui ei ej. Okay, which can be written as E dyadic E u. Note that E dyadic u is a second order tensor where you take a vector, another vector, and do this operation, so that, say for example, if you have A dyadic B, suppose I get say capital C, then the component Cij is equal to Ai Bj. Okay, so this is an operation which is opposite to do what we do by contraction. Okay, so we see that u parallel to E can be determined by this expression. So this is called as the projection tensor parallel to u, or sorry, E. Now if I want u which is perpendicular to E, then this is nothing but, from simple vector algebra, we know that this is equal to u minus u parallel, which means this is equal to I minus E dyadic E u. So the projection tensor in the perpendicular direction is given by I minus I, of course, is a unit tensor, and that when operated on u will give me what is perpendicular or u perpendicular, right. So this is important in many respects. So for example, if you want to look at the stresses that are acting, say normal, if this is the stress that is acting and I want to resolve this into a normal stress and a shear stress, then you can use the projection tensors in order to do that. Okay, you can use that also in eigenvalue problem. Okay, then this projection tensor. So it has quite a few things lined up for it later. So we will do that when we come to that place. Now we will proceed with what we called as the rate quantities. We said that you can distinguish derivatives into two categories. One is what is called as the spatial derivatives, and another is called as the material spatial derivatives. And what we defined as the material derivatives. What is a material or material derivative in the sense material time derivatives and spatial time derivatives? Now the material time derivatives are the derivatives of a quantity, okay, keeping capital X a constant. Keeping capital X a constant. For example, if I have a quantity, say f of x comma t, okay, if f of x comma t, I want to find out the material derivative of this. That means that I can write this down as f of say chi of x comma t, then The material time derivative is obtained by keeping x a constant at a particular x. We will look at this physically in a minute after we derive what this means. As I told you in the last class, we usually write that as d by dt, d, capital D by dt. So d of f by dt, which is the material derivative of f by chain rule, is written as dou f by dou t plus dou f by dou x dou x into dou x by dou t. Yes?
Means that we are not considering the change of material during deformation.
Let me answer that question. What do we mean by this? Just wait a minute. Let us understand this, and then I will explain to you what this means. Which means that the material time derivative has two components, and let us try to understand what these two components are. But before we do that, let us write this down, okay, more neatly in another fashion. This can be written as dou f by dou t plus, what is dou f by dou x? Grad f dot v. Note that now this is a vector grad f dot v. Now let us understand what these two terms mean. Okay. Now in order to understand that, let us look at a physical picture from fluid mechanics. Can be extended to solid mechanics, for example an extrusion problem and so on. Now let us see how we are going to study, say, a fluid flow, okay, through a channel like this. Okay. Now let us now concentrate in this region generally, and more specifically let us look at what happens to that point here, to this point. Let us now follow the velocity of the material at that point. Now there are two things that can happen, or that can be envisaged. One is you focus at that point, okay, see whether that point in space has any change in velocity, okay. That's one perspective. If you really look at it, what happens to a material point, okay, a material point may start here, okay, may flow through this channel, may come here, may come here, may come here, like that. This point may come here, like this, and come to this point, okay. So at that point it might have the velocity at a particular instant what you have noted. So further down it may go, there may be a change in shape, change in velocities and all these things, okay. So the first point, or the first perspective where you look at a point and watch what happens to that point is an Eulerian perspective. The other perspective where you sit on the material and as it goes you capture its velocity is a Lagrangian perspective. Of course, whether it is an Eulerian perspective or Lagrangian perspective, for a material point at that place the velocity is the same. So I am sitting there, say, let's say I am traveling in a boat, I am coming here, you are watching this point, okay, and my boat comes to that point, you capture a velocity, I capture a velocity locally with some device, we will have the same velocities. Now look at it from another point of view. For you as you travel, this is no more a steady state, okay, this is no more a steady state. So you are the material derivative. So as you travel your velocities may change or does change, okay. So your velocities change with time, but at this point of time here for you watching only that point, your velocity may or may not change with time. So from one perspective, the velocity changes with time. From another perspective, the velocity need not or may not change with time. So that is the difference between a spatial and the material derivatives. So you have a point here, and the derivative at that point is given by this term. If this point's velocity changes with time, dou f by dou t changes. Okay, suppose it remains constant as well, then there is a convective term, the second term, which carries that velocity, okay, or the change in this thing. And so the second term is the convective term, and is due to that velocity there. Okay, so that's the difference, physical meaning of the difference between a material time derivative and a spatial time derivative. Spatial time derivative, just to summarize, we are looking at small x. Material time derivative, you are looking at capital X. Okay, and it's very important to realize that as far as the velocity is concerned. Yeah, dou f by dou x dot dou x by dou t. This is just chain rule, so that becomes grad f dot v. Yeah, this is what, so the velocity here is what we call as dou f by dou t. So suppose there is, with respect to time, at that point the velocity changes. Okay, that will also be reflected in the material derivative. Okay, now, so it's a very straightforward definition. Now what happens if I have, this is okay for a field f, what happens if it's a vector field? Okay, note that grad f makes this tensor to jump one order. So what happens if this happens to be, or this f happens to be, say, some function of, say, a vector function of x comma t, okay, then what happens? You would see that dA by dt term here is equal to dou A by dou t plus dou A by dou x dot dou x by dou t. What is dou A by dou x? This is a second order tensor. So in other words, dou A by dou x, if I want to write it in component terms, says becomes dou AI by dou xj. Please note that. So there is a, or in other words, this can be written as again grad A pushing the order of the tensor. Is it clear? Okay. Now, let me define a spatial velocity gradient L. Spatial velocity gradient or spatial velocity gradient tensor, okay, however you want to call it, okay, L to be dou V by dou x. Note that it is dou V by dou x, V and x being vectors, so obviously L is a second order tensor. So L, say, let's say that Lij is equal to dou Vi by dou xj. Note that this is different from material velocity gradient, which is written as dou V by dou x. Now what is this material velocity gradient? Let us see that, let's see what this material velocity gradient is. Write that down. let's see what that is. Please try this, what this is. Which is, of course, you can write that as grad. This is nothing but say capital grad V. You can write that down as capital grad V. Now, what is the relationship between say f dot and this? You can check, just check that, that's what I wanted. Check what is the relationship between f dot and that. Very simple, there is nothing there. That is equal to dou by dou x of, okay, what is V? Dou small x by dou t, okay, which can be written as dou chi by dou t. Okay. Since x is independent, I can switch these differentials so that I can get that as dou by dou t of dou chi by dou x. So, what is this? F dot. What is f? This is f, dou by dou t of that. So, that is f dot. Now, what is the relationship between L and f dot? Very straightforward, it is nothing difficult, just try that out. What is the relationship between L and f dot? Just do a chain rolling, and then, yes, please. Note that L is equal to dou V by dou x, and from here we do that. Okay, then see what that is. I'm deliberately giving you because I want you to remember what all we did. Please look at that. So, if you want, I can help you in one more thing. Dou chi dot, so that is what we wrote there, by dou x by dou small x. F, is it, just have a look at that. Dou chi dot, this is what we just now saw it. F dot, right? And what is this? F inverse, that's all. It's very simple, you know, that's why I wanted you to do it. So, F dot is equal to LF. It's a very important relationship. Okay, F dot is equal to LF. Is that clear? Okay. Now, this L, our velocity gradient tensor, is a very important quantity. And in fact, this is very similar to your ui comma j, which you would have seen in your earlier classes. In fact, you look at that, what it is. Vi comma j. So, L ij is Vi comma j. So, it's very similar to ui comma j. If you remember, in the earlier classes, you had split ui comma j into an epsilon and an omega part, symmetric and a skew symmetric part. You can do exactly the same thing with respect to L. Okay? So, let me remove this. Let's see how we do that. So, L, as I told you, is Vi comma j. Let's say that the symmetric part is given by d, and d is equal to half of, say, Vi comma j plus Vj comma I. And the skew symmetric part is given as half Vi comma j minus Vj comma so that when you add this up, so L is equal to d plus W. D, this D is an important quantity and is called as rate of deformation tensor. It's called as rate of deformation tensor. Rate of deformation tensor. And this omega is called as spin tensor. Note that both D has Dij. Okay, so in fact, you can write that as Dij written in that fashion, omega ij written in that fashion. So rate of deformation tensor and spin tensor. Now, is rate of deformation tensor the same as that of the strain rate, say E dot, or what is the relationship between them? Okay, that's a very important thing again for us to remember. As it is, you see that this guy is more closer, or y more closer. It is a spatial quantity. Now, what is its relationship with E dot? The rate of our green strain. Okay, is there any relationship between them? Of course, there is going to be a relationship, and what it is. Yes, you do that. It's very simple. Let us see some of the small derivations I would like you to attempt, because that makes you familiar with what all we have done so far, and application becomes very simple. They're all very easy. Yeah, I'm leaving out these squiggles. I think I'm sure by now you know which are squiggled and which are not. Calculate a E dot now substitute in terms of the relationship F dot is equal to LF. Substitute that and check what is that you get. I mean, very simple. Is equal to half of F transpose LF plus F transpose L transpose F transpose L transpose L F. Yeah, that is dot of F transpose. This is differentiated with respect to time dot quantity. That's all. Now look at that quantity. This can be written as E dot is equal to half F transpose L transpose plus L F. So what is this? So F transpose, you can bring the half that side here, L transpose plus L divided by 2 F. That is equal to F transpose D F. So E dot is equal to F transpose D F. So E dot is equal to F transpose D F. Right, is that clear? Okay. Now, I have another important thing to derive. I'll give you 2 minutes. You just try it out. It's very simple again. What is the relationship between the spin tensor and rotation, R? Or is it that W dot is equal to R dot? So if you remember, we had seen yesterday, or maybe the last class or before that, we had looked at F very closely. The last class we said that we can split this polar decomposition, and we have F, we have that split up into R and U, and we said that R is a rotation and U is a stretch and so on. Now, that is one rotation. So rate of rotation, if I ask, you may say that it's r dot. Is r dot same as w, which is a spin, which I called a spin tensor? Or in another fashion, or in another way, we can say that f I had very neatly decomposed into a rotation tensor and a stretch tensor. Is it that this L had been additively decomposed in a very nice fashion like that, and is it that we have in D a quantity which represents purely stretching, and do we have that quantity W to represent only the rotation? That's a very important thing to understand. Okay, do these two types of deformations or splitting of the deformations, does it lead to the same result? So let's see that. Let us see what is the relationship between r dot and W. Okay, so I'll give you two clues. Let us see. You start that r transpose is equal to I. Okay, and that f is equal to r u. That's the first step. Then substitute in L and the next relationship. L is equal to what? No. We just now derived in terms of f dot f inverse. Now we have these three equations. Let us see how you can calculate that. Okay, these three expressions. This is a problem which I am giving you. Let us see how you do that. So in other words, if you want, r dot f dot is equal to r dot u plus r u dot. Okay, that also I am writing. Substitute it back into L. L is equal to r dot u f inverse. So L is equal to r dot u f inverse plus r u dot f inverse. What is u f inverse? What is u f inverse? We had f is equal to r u. So u f inverse so this can be replaced by r transpose, okay, r u dot f inverse. Now from the first expression here, you have r dot r transpose plus r dot transpose equal to 0. Substitute it. Let's see. I'll just stop here for a minute, continue, and let me know. Now what I want you to do is very simple. Now that I've written L, okay, now that you have an expression here, write down the expression for D and this omega r w, small w. Okay, write down an expression for these two and tell me what the expression is. That's all. If you want, you can replace this by u inverse r transpose, because r inverse equal to r transpose is what we are using there. Now if you want next step also, I'll give you a clue. What is D? Yes, half of L plus L transpose is what it is. Calculate L transpose, okay, and then use the first equation r dot r transpose plus r dot transpose is equal to 0. This one, yeah, obviously, because r transpose is equal to I, differentiating with respect to time and being I, obviously, it's very straightforward. So, yeah, this is what I define. L transpose plus L or L plus L transpose, whatever it is, it's all the same. So, this is r dot r transpose is equal to minus r dot transpose. Okay. So, now write down, say for example, D, what would be the values or what would be the half r u dot u inverse, yes, plus u inverse, yeah, yeah, because it's symmetric, u inverse u dot r transpose, right? Very good, fantastic. So, what is W? Write down W. Same way you write down W, that's all, nothing. First term, if you want, I will write down r dot r transpose plus, that's the first term which you would get. That term went off because of this when I took the symmetric and antisymmetric case. R dot r transpose plus, yeah, half of r, yes, u dot u inverse minus u inverse u dot, very good, r transpose. Right, that's all, very simple substitution. Now, what I want to do is to focus on, say, this term. Look at this term. This term here involves not only r but also u. If I had stopped it with this term, first term, then W depends only on rotation. So, W is not a pure rotation, but it involves stretch. So, D is not pure stretch, but also involves R and R transpose. So, both of them are not pure stretch, it's not stretch rate, it's not U dot. What I want to bring out by this is clearly that D is not just U dot, W is not R dot. Okay. This is a very important thing to remember. Okay, that the spin tensor is not only depends upon R.
What is that spin tensor actually means in the physical context?
Yeah, so the spin tensor is not the same as that of just stretching and rotation. It has rotation plus, okay, stretching, okay, terms which are involved like this, and then a rotation. So it's a combination. You can't give a simple physical explanation. Yeah, it's a mathematical thing. You can't give a simple physical explanation like what we did yesterday. But it has a rotation part and a stretching followed by a rotation part. Okay, so both of them are involved. That's what this means. Okay. So before we go further, I just want to define one more small thing, okay, with respect to F, because we have to go and define stress tensor. I want to define one more term called F bar. Okay, you have a lot of terms, I understand that. Okay, so one more term which we will define, what is called as F bar. F bar, you will see what it is in a minute. Has a very important connotation in incompressibility conditions. If you really look at determinant of F bar, this is determinant of f, and determinant of j minus 1 by 3 f now becomes this being 3 by 3 will become j inverse f. Okay, so j inverse determinant of f. Now determinant of f being equal to j, determinant of f bar is equal to 1. Okay, so this is from simple theory of determinant, we get that determinant of j power minus 1 by 3 f, because this is being 3 by 3, you will multiply every term by j, so j inverse determinant of f, so that equals 1. So what does it mean? It means that f bar is the one which is responsible for dilatation, and when there is incompressibility when determinant of f is equal to 1, which means or j, I mean this in other words, this is the one which talks about, or we can let me put it like this, we can split f into two parts. One is the dilatational part and the deviatoric part, and when determinant of f bar is equal to 1, we say that this is the deviatoric part of f, and the other part j power minus 2 by 3 is the one which gives you the dilatational part of f. So in other words, f can be split into two parts like what we do for stress, the dilatational and the deviatoric part. Okay, so this can also be split into two parts, okay, the dilatational and the deviatoric part. Okay, so it's pure isochoric deformations are defined by f bar. Okay, so with that background, let us now look at what are called as stress tensors. Now, we have seen that there are number of or various strain measures that we have used, number of strain measures. Okay, in fact we generalized the whole thing. We said that half u power n minus 1, where n takes different values, can be used as a strain measure. In fact, when n is equal to 0, people define the strain measure to be ln of u and so on. In fact, why all that? Now, stretch also we saw can be very useful to us to define deformation. Like that, there are a number of stress measures that are now going to be defined. All of us are familiar with the Cauchy stress, sigma. We had used that in the earlier course. Okay, we were not worried about change in the area and so on, because all of the deformations which we had considered till now are infinitesimal deformations. But now since we are looking at finite deformations in the sense that there is a change in area, and in fact we had a formula which connects ds and capital DS being the original area, small ds be the final deformed area. Okay, we now know that this area difference before and after deformation has also to be taken into account. In fact, you would have done in your undergraduate course, say strength of materials, or maybe in material science, you would have defined what is called as the true stress and engineering stress. What did you do there? What you did was very simple. Whether you took the original area or the current area, you called that as a engineering stress or nominal stress, and if you had taken the current area, you would have called that as the true stress. For Cauchy stress is nothing but the true stress. Cauchy stress is nothing but the true stress, and we have an equivalent stress measure in the multi-axial case for the nominal stress. So, number one, we have Cauchy stress well defined. We have an equivalent stresses for the nominal stress. That is the second definition of stress and I call that in the multi-axial case as the first pure law Kirchhoff stress. First pure law Kirchhoff stress. Let us say that I cut a body like what we used to do last course on the definition of stress, and let's take a small element. Okay, let us define the area same fashion as we did the last class when we derived Nansen's formula. So let me call that as, say, D capital S. Let there be, okay, of course this is X, let there be deformation, and let us say that okay, deformation takes place and this point goes to small x, and let the area be d small s. Let that infinitesimal force that is acting in that area be force vector be df, okay, and we know how to define the stress. In the earlier class we had defined this as delta f, or we had defined it as delta f by delta s limit as delta s rather goes to 0. Okay. So in this case we say that let this be the normal. Of course this also has a normal, let me call that normal as, say, n. Then df being the same, okay, that's acting in that small area because it's an infinitesimal area, you can define sigma n ds, which gives me df in the deformed coordinate to be what? Let me call that as p n ds. Okay. So sigma is a quantity which is associated with the current or the deformed coordinate, and p, of course this is also a tensor, is one which is associated with the reference coordinate system. But what is ds? We derived it in the last class. What is ds? J f inverse transpose, yeah, so n ds or d capital S, I mean d capital S, which is a vector. So d capital S, which is a vector, can be, okay, this is nothing but d. Yes. So this is actually d small s. Substitute that into that expression, see what you get. Sigma, so J can be out here, F inverse transpose n ds is equal to P n ds. Comparing the left hand side and the right hand side, obviously P is equal to J sigma F inverse transpose. So the PLO Kirchhoff stress can be calculated from the Cauchy stress, and the vehicle for this calculation is nothing but the Nansen's formula. So P is equal to J sigma F inverse transpose, or sigma is equal to J inverse P F transpose. So we want to write that this side, bring this side, so that becomes J inverse, bring it the other side, so this becomes F transpose, that's equal to sigma. So the second stress measure now we have learnt is first Kirchhoff stress. The third stress measure which comes directly from here is called as Kirchhoff stress. Note the difference between first Kirchhoff stress and Kirchhoff stress. In fact, I am going to define the next class what is called a second Kirchhoff stress. Okay. So Kirchhoff stress, which is usually denoted by tau, is defined as J sigma. So tau is called as Kirchhoff stress. Right? Now, we know sigma is symmetric. By this definition, we know Kirchhoff stress is also symmetric. The question is whether Kirchhoff stress is symmetric. This being symmetric has very important connotations in our computational techniques because you can save a lot of space and efforts and so on. So let us now check whether first Kirchhoff stress, which is nothing but the equivalent of a nominal stress, is it symmetric? So in other words, since sigma transpose is symmetric, so this becomes say J inverse F P transpose, which means that P F transpose is equal to F P transpose. Not P is not equal to P transpose, but P F transpose is equal to F P transpose, which means that the first Kirchhoff stress is not symmetric. So though the definition is very straightforward and nice, first Kirchhoff stress is not that very useful to us in computational situations. But the concept is very important to understand. And we will continue with our concepts of stress, other stress measures, and so on in the next class.